Okay, in this last video, I'm actually going to start you off with a joke, okay? So this is kind of a funny one I heard in college, and hopefully you're not offended by it, but this is how the joke goes, okay? So there are a group of mathematicians and a group of physicists, and somebody takes them out to a football field for a little thought experiment, okay? And I'm just going to draw this out for you so you can kind of visualize. Okay, so here's our football field. Now, on one side of the football field, they put some girls over here. And they put all the mathematicians and the physicists over here. I just realized that this isn't very politically correct. So let's say that these mathematicians can be boys or girls, because we all know that there's tons of awesome female mathematicians. And then these are just somebody they're attracted to on the other side. Okay, that way, you know, we want to be inclusive of everybody. So what's going to happen is they say to these mathematicians and these physicists, okay, you are going to go to this other side, but you can only do it by having the distance between you and the person on the other side. Okay, so what that means is you can walk half the distance to them, right? And then after that, you can walk half that distance. And then after that, you can walk half of that distance. And then after that, you can walk half of that distance. And then after that, you can walk half of that distance. And then after that, you can walk half of that distance, and so on. And the question is, will you ever be able to get there? Okay, so the mathematicians say, you'll never be able to reach the person on the other side. And the physicists say, you'll never reach the people on the other side, but you'll get close enough for practical purposes. That's the punchline. All right, so again, it's kind of an old-fashioned story, and the idea is to kind of make fun of mathematicians and physicists. The idea that mathematicians are so precise and like exact, and physicists more try to use math to like quantify the world. So they're like, look, you're going to get close enough. It's fine. You'll be able to, get to the other side. But this kind of brings up an idea of a convergence and an infinite geometric series and how it works. So let me kind of explain how that works. Okay. Let's say that this football field is just one unit, one football field, okay? So let's make a series, and let's talk about the distances, okay? So if I want to, try to make it from one side of this football field to the other, what I have to do is I'd have to start with the first move. So the first move was going half the distance, right, of the football field. You went half the football field. Okay, then the second move is to go half of half, right? So you have half left, and you're going to go half of that distance. So that's a quarter of the whole football field. Okay, so now you're here. Your next move after that is to go half of the rest of the distance. So the remaining distance is a fourth, and you can go half of that, which means you're going to be adding an eighth to your total distance. Okay, now that you're at that space, the next, you can half that eighth, which means you can go a 16th of the distance. Okay, so this is your sequence, or your series, excuse me. So you can see the pattern. Every time you're multiplying by a half, right? A half, a fourth, an eighth, a 16th. So R is equal to a half. Oops. In our sequence, and then you can say like A1 is equal to 1/2. So we're multiplying, and then we're going to add them all up. Okay. Now here's the question for you. Here's where it gets a little bit theoretical. I'm going to add numbers infinitely many times, right? So the mathematicians say you're never going to get to 0, right? If you keep having 1/32nd, 1/64th, 1/128th, 1/256, you're going to get smaller and smaller and smaller, but you're never actually going to get to 0. Right? You're never going to stop getting smaller. You can always half what you have before. And so this sequence is never, ever going to end. It's just going to keep on going and going and going and going and going. But the idea is there's still a limit to how far you can go, right? You're never going to get past this guy. So even if you keep adding distances, if the distances you're adding are getting infinitely smaller, you can still have a limit to how far you can go. So the sum of this series is actually 1. And in this case, the sum is more like a limit, right? And then these get infinitely smaller, but they never stop. And theoretically, if you add all those up, you kind of get to the end. You get to the end zone. But you're never really going to be able to go past it. There's like a limit to how far you can go. Okay, so this is an infinite geometric series, but you can still find a sum to it because there's like a limit to how far you can go, right? You're never going to get past this end zone because you're always halving the distance to the end zone. So that's the idea. So when you have a geometric series and r is less than 1, actually what they say is absolute value of r is less than 1 because you can have like a negative half or whatever. You're basically going to have a series that you can find a sum for. Okay? The word for that is that it converges. The series converges. Whoops, there. Okay? So when absolute value of r is less than 1, that's like a decay factor, right? It's like when your multiplier is bigger than 1, you have exponential growth. When your multiplier is less than 1, you have exponential decay. So when you have an exponential decay, you have a series that converges. In other words, your pieces are getting smaller and smaller and smaller and smaller, and so you have a limit to what you can add up to. Okay, well, one more way to think about this theoretically, and then we'll actually get into the practical part of this. What does an exponential growth curve look like? Looks like this, right? You have what we called an asymptote, a number that this graph approaches but never quite gets to, okay? That's kind of like what's going on here, right? We're having, these numbers are getting closer and closer and closer to 0 without ever touching 0. And so what you're doing is you're adding very, very, very small numbers after a point, and they're getting infinitely smaller, but there's still infinitely many of them. And so even though the numbers are getting closer to 0, you can kind of theoretically add them up and say, look, I know I can't add up infinitely many things, but there's a limit to how far these things are ever going to get. And so I can kind of use that idea of limit as a sum for this sequence and say, well, theoretically, if I added all these numbers up, this is the biggest number you can possibly get. And the sum is getting closer and closer and closer to this. So that's your sum. Okay, so those ideas in there, the idea of like infinitely many small pieces, adding them infinitely many times, those are some calculus ideas. So you're going to see these often. You're going to see these again. You're going to see these in 1050. You're going to see these ideas in calculus if you end up taking them. So they're kind of important theoretically. Okay, so you can add up infinitely many things and get a sum. The idea here is that the sum is more like a limit. Right? It's approaching this number, and it's never going to get bigger than that number, but you're adding, infinitely many smaller pieces that get smaller and smaller and smaller, close to 0. So notice how these are fractions, right? They're getting smaller and smaller. So here's the formula that you need to use. It's the sum of an infinite geometric series. So S of infinitely many terms. So we don't put a number here because we can't put a number here. It's not like 10 terms or 20 terms or even 100 terms. There's infinitely many terms, okay? But it's going to be 1 over, the one's on the bottom. It's A1, the first term, over 1 minus R. Now, this formula, I could show you where the derivation comes from, but I feel like doing one derivation, one like big theoretical conceptual idea per lesson is probably the max that I can do. If you're familiar about where this comes from, you could look it up and kind of figure it out, but this is kind of what's going to happen here. So let's use this formula on some practice problems. So this is ... There's no number of terms. This is an infinite geometric sequence, and the idea is there's going to be some limit that this can hit, because we're adding smaller and smaller pieces. So we need to find A1, which is 6, and we need to find R. So that can be a little bit tricky. Let me show you a couple ways to do it. Okay. Now R stands for ratio, so you can always do this some number divided by the one before it. So if you did 3 divided by 6, that'd be 3 over 6 or 1/2. That'll work. You can also do it in 2 pieces. If you look at 2 fractions, you can say, well, what am I multiplying by on the top? So how do I get from 3 to 3 by multiplying? It's times 1. How do I get from 2 to 4 by multiplying? It's times 2. So it's times a 1 on the top and a 2 on the bottom. So you can kind of think of it as like your top series and your bottom series, and then write your R as like the top R divided by the bottom R. But either way, it's halving, right? So what we have here is we have the first term, which is 6, divided by 1 minus a half. Okay, so that's 6 over, and if you want to do common denominators, you got that, and then you have 2 over 2 minus 1 over 2 is 1 over 2, and then you got invert and multiply. So a number divided by a fraction, you keep, change, flip, or copy dot flip, or invert and multiply, or multiply by the reciprocal, or however you want to remember that. So you have, multiply by the reciprocal. Okay, so 6 over 1 times 2 over 1 is 12 over 1. Okay, so this is getting closer and closer to 12. So 6 plus 3 is 9, plus 1.5 is 10.5. Plus 0.75, right? It's getting closer and closer and closer to 12. But since the pieces you're adding are getting smaller and smaller and smaller, it's never going to get past 12. Okay? So you can do that same thing on these guys. You just got to find your first term, which is pretty easy. You got to find your R, which, can be a little bit tricky, but, what are you multiplying by on the top? It's a 1. What are you multiplying by at the bottom? It's a 4. Okay, so R equals 1/4. So take 2 successive fractions, and that's the easiest way to do it. Okay, so 1 over 4, and then you just plug everything in. Okay, just for fun, let's go and find out the sum of this guy. Since we're looking at this this theoretical, we started with this joke. So A1 is equal to 1 over 2. Okay, and R is equal to 1 over 2. So our sum, infinite sum, should be 1 over 2 divided by, so that's A1, divided by 1 minus 1 over 2, which is 1 over 2 over 1 over 2, right? So you can kind of see where this is going. It's going to be 1, right? So invert and multiply, 1 over 2 times 2 over 1 is 2 over 2, which is 1. Yeah, so the sum of this guy, a half plus a fourth plus an eighth plus a 16th plus a 32nd, it's 1, right? You're never going to get farther than 1 football field length if you're walking half the remaining distance every single time you move. So that's some conceptual ideas about converging series and infinite geometric series that you'll probably see in the future. The conceptual idea is important. You're going to use it later. Right now, though, if you don't quite understand that, or that's a little confusing, you got your formula right here, which is also on your formula sheet. Now notice that we don't have you don't have a sum formula for an infinite arithmetic sequence or series. And think about that for a second. If you're adding the same number every time, then your sum is always getting bigger. There's no limit to how big it can get. It's always going to be getting bigger. The difference here is that we're adding smaller and smaller and smaller pieces. Here, we're adding the same size piece every single time. And so this will never converge. This will not have a limit, which is why we don't have a formula here. So there's only formula for a geometric infinite series, and it's only if it converges. So one thing we should add is this only is going to be relevant if R, the absolute value of R, is less than 1. In other words, it's an exponential decay. Your decay factor, or your multiplier is less than 1. It's getting smaller. Okay? All right, that should do it for this one. That's your last kind of homework assignment that we're going to have. The rest after this is going to be review and getting ready for the final. So hang in there. You basically made it. So take the final. Make sure you study, get a good grade on that, and that's it.